section 7.5, page 535. They start off here in 535 telling us that many applications in business and economics involve a process called optimization, in which you're asked to find the minimum or the maximum value of a quantity. Like a business would want to maximize their profit or minimize their costs. That's the type of thing that we're looking to do in optimization. And one optimization strategy is called linear programming, and that's what we're looking at today. It says a two-dimensional linear programming problem will consist of a linear objective function. So our objective function is just what we're trying to accomplish. Like if you're trying to maximize your profit, if that's your goal, that's your objective, then your objective function is going to be the profit function. If you're trying to minimize your cost, that's your objective, and so your objective function would be the cost. Then they're also going to give me a system of linear inequalities, just like we were working on our last section. They're going to give me a system of linear inequalities called constraints. I'm going to graph that system of inequalities, just like we were doing in the last lesson. And when I'm done, remember that I got either like a bounded region or an unbounded region where every single point within that region was a possible solution. The textbook calls that for linear program, they call that the set of feasible solutions. Now, there are an infinite number of possibilities in those regions. So how am I supposed to test all of them to figure out which is the absolute highest or which is the absolute lowest? Well, this is a really nice thing. The very last sentence they tell me there is that if there is an optimal solution, a maximum or a minimum, it must occur at one of the vertices of that region. So all I'll have to do is just pull out the vertices and plug them into my objective function and see which one gives me the absolute highest value or the absolute lowest value, whichever one that I'm looking for. All right, makes a whole lot more sense when we see one. So let's look at example number 1. For example number 1, they tell me find the maximum value. So that's my objective. That's what I'm trying to do. Find the maximum value of z is equal to 3x plus 2y. So that's my objective function under the following constraints. And they gave me 4 constraint equations or inequalities. And you'll notice that that's just a system of inequalities. So let's graph that system exactly like we were doing in section 7.4. All right, so let's start with x is greater than or equal to 0. We said that if you were going to graph an inequality, to treat it just as if it said equal to. So what does x equals 0 look like? Yes, vertical line at 0. Is it going to be dotted or solid? Solid, because it's got an equal to with it, right? Remember we said if it was less than greater than, it would be dotted. If it was less than equal to or greater than equal to, then it would be solid. And then where are the values that are greater than 0? Am I going to shade to the right or to the left? Right. To the right, absolutely. So there's x is greater than or equal to 0. Vertical line at 0, solid, shading to the right. Now, I'm going to go through and use like red, green, blue, and black. You're welcome to do like vertical lines, horizontal lines, diagonal in one direction, diagonal in the other. You can use highlighters, markers, colored pencils, whatever you want to use. All right, then let's look at the second one. Y is greater than or equal to 0. How does y equals 0 graph? Horizontal line, right? Horizontal line at 0. And it's going to be solid because it's equal to, or are we going to shade above or below? Above. So if we do, this is what we'll get. And remember that solution equals intersection. So right now, where are my two inequalities intersecting? 0. Yeah, in the first quadrant. So if I wanted to, I wouldn't have to, but if I wanted to, I could go through and clean this up a little bit, because I could go through and erase off any values that weren't a possibility. So you don't have to. I mean, if you're using pen or something or markers or something, you're not going to be able to do that. But if you want to just clean up your region as you go, you're welcome to. You don't have to. Now, those two constraints, x is greater than or equal to 0, y is greater than or equal to 0, are going to be constraints for almost every problem that we work with, particularly when we get into real-world applications, because you can't make a negative number of CD players, right? You can't make a negative number of t-shirts. So when you're talking about a product, it's always going to have to be greater than or equal to 0. They will not always state those two equations, though. Sometimes, based on the information given in the problem, they'll expect me to assume that on my own and come up with those two constraints on my own. They won't always be stated. So think of those as like 2 freebies. Don't forget about those. Be sure that you include those. Additionally, because we've graphed this now, where we've gone through and seen that x is greater than or equal to 0 and y is greater than or equal to 0 only intersect in the first quadrant. That makes sense because the only place that x and y are both positive is the first quadrant. Then when we see that on subsequent problems, you do not actually have to go through and shade horizontally and shade vertically and erase off the excess. For me, I'm perfectly fine with you, just working in the first quadrant without having to show me all of that work. All right, so let's look at the next one. We've got x plus 2y is less than or equal to 4. So again, I'm going to graph that just as if it said equal to. So if I were graphing that line, I would make an xy chart and I'd find my x-intercept and my y-intercept. So I'd put 0 in for x and find y is 2, and I'd put 0 in for y and find x is 4. The key for drawing these is going to be precision. So you definitely want to draw these on graph paper. You want to use a straight edge and be as precise as you possibly can. Because remember, the vertices are going to be your solutions. So if you don't draw it accurately, you're not going to come up with the right vertices. All right, so once I had my solid line, then I can go through and pick a test point to figure out which side to shade. So I use 0, 0. So if I plug 0, 0 in up here, I'll get 0 plus 0 is less than or equal to 4. That's true. So that let me know that I was going to shade down below. So right now, if I'm looking for where I have red and green and blue, or where I have horizontal and vertical and diagonal, it is just this little triangular region. That's my region of feasible solutions right now. All right, then let's look at the next one. We've got x minus y is less than or equal to 1. So again, I'm going to graph that as if it said equal to. So I'm going to put 0 in for x and 0 in for y and find my x and y intercepts. Now, I got 0, negative 1, and I don't have a negative part of my graph down here, and I don't want to try and approximate it because then that's going to make my graph be off possibly. So I'm just going to find a different point if I hit a negative value since it's not on my graph. So I just plugged in another value, and so I'm going to plot 1, 0 and 2, 1. So again, using a straight edge and being as precise as I can be, that's going to give me this line. I picked a test point of 0, 0, and when I plugged it in, I got 0 minus 0 is less than 1. That's true. So that let me know to shade up above. So wherever I have all 4 colors or all 4 shadings is going to be my region of feasible solutions. In this case, it's a bounded region, and it's that little highlighted guy. All right, so now I want to pull off my vertices because every single point in that highlighted region is a possible solution. I mean, I could be here for eternity plugging in points because there's an infinite number of them. Instead, they've told me that my maximum or minimum is always going to occur at one of the vertices. So let's identify those vertices. All right, so some of them are pretty easy to see. Obviously this guy's 0, 0. This one, if I was unsure what that was, if my graph was unclear, I could always go back and say that's the x-intercept I got from the black line, so I could come up here and go, oh, okay, the x-intercept was 1, 0. Same story over here, I could say, okay, that's the y-intercept I got from the blue line, so I could come up here and go, that y-intercept was 0, 2. So the only one that might be a little bit iffy is this point right here, and if I've been very precise in drawing this, it should be going right through that corner and be clear to me that that vertex is 2, 1. Now, there will be times that it will be hard to tell what the vertex is. We're going to see that in the next example, and I'm going to give you some strategies for what to do if that happens when we get there. Okay, so let's take those 4 vertices that we just got, 0, 2, 0, 0, 1, 0, and 2, 1, and let's plug them into our objective function. So I'm going to go through and plug in 0, 2. So I'll put 0 in for x, 2 in for y. And then I'm going to plug in 0, 0. Then I'm going to plug in 1, 0. And then I'm going to plug in 3, 1. Sorry, 2, 1. Now, if I were looking for the minimum is obviously 0. They asked me in this particular case to find the maximum. So I'm looking at 4, 0, 3, and 8. 8 is the largest value there. So my maximum is going to occur when x is equal to 2 and y is equal to 1. And that would be my answer. So now that I've seen one of these problems, when I go back and read those directions on 535, it makes a little more sense to me. And on the bottom of 535, they give me some steps. It says, number 1, sketch the region corresponding to the system of constraints. The points inside or on the boundary of the region are feasible solutions. So that's what we did right here when we graphed all 4 of our system of inequalities, and that gave us that region of feasible solutions. Then number 2, it says find the vertices of that region. And then number 3, test the objective function at each of those vertices and select the value of the variables that optimizes the objective function. That just means that finds the highest value or the lowest value, depending on if you're looking for the maximum or the minimum. One of the most common mistakes that students make with this is they try to use the objective function while they're graphing. We do not graph that objective function. We do not use it until the very end. We only use it to plug our vertices into to find the maximum and minimum. We do not graph it. All right, so they go through in the textbook, that was example 1. They go through and give you several more examples of the exact same thing. So if you'd like some additional ones to look over and play around with, they do give you examples 2, 3, and 4. Example 5 shows us the real-world application of this and what we could do with this. And so that's the next thing we want to look at. So example 5 says, a manufacturer wants to maximize the profit for 2 products. Product 1 yields a profit of $1.50 per unit. Product 2 yields a profit of $2 per unit. Market tests and available resources have indicated the following constraints, and then it gives me 3 constraints. They didn't give me an objective function or constraints. They have put it into a word problem form, and in this case, I have to create my objective function, create my constraints, and then I can begin that process we were just doing in example 1. All right, let's start with the objective function. What is my objective? What am I trying to do? Maximize the profit. Right, I'm a company. I want to maximize my profit. So my objective function is going to be a profit equation. So you can see here our objective function is going to be whatever the profit is equal to because I'm trying to maximize that. They also told me that there were 2 different products that I was using, and I want to know how many of each of them to make to maximize my profit. So I'm going to call the first one X and say that X is the number of product 1 units that I should make to maximize my profit, and Y is the number of product 2 units that I should make to maximize my profit. Okay, so let's think about that profit a second. It says product 1 yields a profit of $1.50 per unit. So if I sell 2 of them, how much profit do I make? $3. How do we get that? Yeah, 1.5 times the number of things that I was selling, right? The number of product 1 that I'm selling is X, right? So for the profit on that first product, it's just going to be 1.5 times X. All right, then it says the profit on the second type of product is $2 per unit. So how would I write that profit? 2Y, right? So if I want my total profit, add, subtract, multiply, divide those 2. Add, right. So I want to take the profit that I get from product 1 plus the profit that I get from product 2. When I add that together, that will be the total profit that I make. That's my goal. I want to maximize that. I am not going to touch that equation until the end of the problem when I plug the vertices in it. I don't graph it or do anything else with it. All right, now I need some constraints to create that region of feasible solutions. They give me 3 in the textbook, but there are actually 5. What are the 2 hidden constraints? Yes, x and y are both greater than or equal to 0. You cannot make a negative number of products. So they won't state that. They won't give you any clue about that at all. But those two are absolutely, those are just freebies. They are part of my constraints. Okay, so let's look at the three things they did tell me, starting with number 1. The combined production level should not exceed 1,200. Okay, let's start with combined production level. What does that mean? X plus y, right. Should not exceed.
Should be less than.
Less than, could it be equal to? Yeah, it just can't go over, right? But it could be less than or equal to 1,200. So that's our first constraint. X plus y is less than or equal to 1,200. That's the most that my plant can put out in one day. So it doesn't matter what the supply and demand are. It doesn't matter how many people want to buy it. I can only manufacture 1,200 total a day. All right, number 2 says the demand for product 2. How could I represent that? Y. The demand for product 2 is no more than? It has to be less than or equal to, right. Half the demand for product 1. 1/2 x. Perfect. So y is less than or equal to 1/2 x. There's my second constraint that they gave me in the book. All right, number 3. The production level of product 1, x, is less than or equal to, 600 plus, 600 plus, 3 times the production level of product 2. 3y. Good. So we could say the production level of product 1, x, is less than or equal to 600 plus 3 times the production level for product 2. All right, now we've created our objective function, our constraints. Now we're right back to where we were in that last example. Okay, so we're going to start off with x is greater than or equal to 0 and y is greater than or equal to 0. I told you that you didn't have to graph that for me, but I'm just showing you that we're starting with that. All right, then we've got x plus y is less than or equal to 1,200. So I'm going to treat that as if it said equal to. So I'll put 0 in for x, and I'll get 1,200, and I'll put 0 in for y, and I'll get 1,200. So I'm going to count by 100s down here. So I'm going to come over to 12, 0, and come up to 0, 12. I'm going to use a straight edge, be as precise as I possibly can be. I pick a test point to see which way to shade, and I pick 0, 0. So when I plug that in, I get 0 plus 0 is less than 1,200. That's true, so that lets me know to shade down below. So you can see our shading down below. So right now, our region of feasible solutions is that highlighted triangle. All right, then let's look at the next one. Y is less than or equal to 1/2 x. So I'm going to go through and put 0 in for x, but when I do, that also gives me 0 for y. So I'm going to have to come up with another point. There's nothing magical about this one. I just went, since, x goes from 0 to 1,200, I wanted something kind of in between. So I just went halfway in between and put in 600 for x and got 300 for y. So I'm going to plot 0, 0, and I'm going to plot 600, 300. And again, I'm using a straight edge to be as precise as I can be. If I pick a test point, I can't use 0, 0 this time because that's on my graph. So maybe I want to come over here and use something like 300, 0 or something like that. Okay, so if I put 0 in for y and I put 300 in for x, half of 300 is 150. So I get 0 is less than 150. That's true. So that let me know to shade down here. So the only place where all 4 of my constraints are overlapping is that highlighted triangular region. Something that'll be really helpful for you later on is if while you're graphing, you label the line that you're graphing with its equation. And we'll see why that's helpful in just a minute. All right, so then our last one, we want to graph x is equal to 3y plus 600. When I put 0 in, I got a negative value. And again, like I mentioned before, I don't have a negative graph down here. And I don't want to try and hand draw it and make my graph be inaccurate. So I just found a couple other points. I did plot a lot of points before I found these two because I was trying to intentionally get something that wouldn't plot in the middle of a box. Like I don't want to be plotting 627 or something crazy like that. So I did go through until I found some values that would land right on a corner of a block so I could be really precise in my graph. And again, I'm going to use a straight edge and graph our line. I picked a test point of 0, 0 and plugged it in, and I got 0 is less than 600, which is true. So that let me know that I was going to shade above. And so that left us with this highlighted region of feasible solutions. So it ends up like a big mess. That's why I mentioned if you wanted to use, colored pencils or something and erase it off if it made it easier for you to see, you're welcome to do that, but you don't have to. All right, so now we want to try to identify our vertices. Some of these really easy to see, okay? So it's really easy to come up with 0, 0. It's really easy to come up with this guy because even if I couldn't tell what it was, I could say, okay, that's the x-intercept that I got from this equation, so that's got to be 600, 0. But these other two might be a little more difficult. If I've graphed really carefully, this one's landing exactly on a block, so it's pretty obvious that it's 800, 400, but this is my problem right here. I have a dot in the middle of a block. And no matter how accurately I graph, that's going to happen sometimes. It looks like it's kind of halfway in between 1,000 and 1,100, so that it might be at an x value of 1050. And it looks like it's kind of halfway in between 100 and 200, like it might be at a y value of 150. So that would be my guess, would be 1050, 150, but I honestly don't know. So how do I figure it out if I have a vertex and I'm not sure exactly what it is? Let me give you a couple of suggestions. Here's what I would try first. Remember that point is the intersection of this x plus y equals 1,200 and this 3y plus 600 equals x, right? That's why it's helpful to have them labeled like that. Intersection equals solution. So where they intersect is the solution of that system. If it's a solution for that system, that means that when you plug it back into those two equations, it works, right? It makes both of them true. That'd be the first thing that I would try. I would just try taking what I think is the solution and plug it into those two equations that are intersecting at that point. If it makes both of those equations true, which it did here, that's the point. That's the vertex. I don't need to do anything else. If I plug in and it doesn't work in one of those two equations or both, that is not my solution. That's not my vertex. Okay, great. Then how do I find it? Well, if that is just the solution to that system, come up here and solve the system. I could solve it by substitution or by elimination, whichever I preferred. You'll notice I solved by elimination and it spit out for me y is equal to 150 and x is equal to 1050. So if I ever have trouble finding one of my vertices, that gives me a couple of ways that I can attack it to come up with it. Okay, so now I've identified my four vertices. I've got 0, 0, 600, 0, 1050, 150, and 800, 400. Now I use my objective function, but not before. So I'm going to go through and plug in my four vertices, and I'm looking for the one that gives me the maximum value because I'm trying to maximize my profit, right? So when I get 2,000 right here, that's the largest of all of my values. That is going to be my maximum profit. So it depends on what they ask me to find. If they say, what is the maximum profit? Then I would say 2,000. More likely they're going to say, how many of each product do I need to make in order to maximize my production? So in that case, X was 800, so that means I need 800 of product 1, and Y was 400, so that means I need 400 of product 2. It's just whatever they ask me for in my answer. All right, so these are very time-consuming problems. We're not going to do many of them. As a matter of fact, we're only going to do 1, 9, and 41. And before you panic because I'm giving you 3 of them, let me show you 1 and 9. For number 1, they give you the objective, they give you the constraints, they give you the graph. All you have to do is pull off the vertices and plug them in, right? Same story with number 9. They give me everything, I pull off the vertices, and I plug them in. It is not until I get to number 41 that I'm doing a problem exactly like we did here, where I have to come up with the objective, the constraints, everything. Because that is the only one that we're doing this whole process on, you cannot come in tomorrow and say, I didn't know how to set up the equations and I have a question mark. That doesn't count for attempting the problem. You have to have some type of a graph for number 41 in order to get credit for attempting that problem. Okay? And as I mentioned to you, don't go buy a tablet of graph paper. You can just download a sheet or two. Just Google, free downloadable graph paper, print out a couple of sheets. Try and get the big block graph paper, though. It'll make it easier for you. Okay?